Hello, welcome to another episode of Q&A about history of science and technology. So let's see. I was a bit distracted because we're right in the middle of both an intense product release process and also a bunch of science that I'm doing. But this is a good relaxation, he says. So let's see. We have a question here from Hannah. Can you tell us anything about the history of quantum mechanics? Well, 1925 was sort of a big year for quantum mechanics. So we're heading for the centenary of what was sort of the year of the creation of quantum mechanics. But let's tell a bit more of the story. So the idea that things could be discrete in the world is an idea that existed from antiquity. This was people like Democritus, the Epicureans. They were all, the world is made of atoms. They had the really good idea that everything we see could be made of different arrangements of the same kind of thing. So that was sort of a first kind of notion. Then there was, for a long time, discussion, is light discrete or continuous? The first sort of, I would say, the big kind of by the 1800s, things were kind of, okay, we've really got to figure out, are things discrete or continuous, particularly for matter? And there was there were sort of two lines of development there. One was about chemistry and about observing that there were sort of integer multiples of different amounts of material that occurred, and that sort of suggested that things like water might be two hydrogens and one oxygen, rather than a continuous amount of hydrogen, a continuous amount of oxygen type thing. The other was work on thermodynamics, on the characteristics of heat, the question of what heat was, and the question of whether heat was somehow associated with microscopic motion or whatever else of discrete molecules. And the big person who pushed that was Ludwig Boltzmann. This is 1860s, 1870s, was kind of, yes, this is a way of understanding thermodynamics. And he had a whole kind of development of sort of an atomic-based theory of how that kind of thing worked. It was also picked up by people like James Clerk Maxwell and so on. But people didn't generally believe it. Even though there was a bunch of mathematics that got worked out about thermodynamics and so on, that was based on kind of this atomic theory of gases, it was generally, but really we know that heat is this continuous fluid, and really we don't have to have the atomic hypothesis for matter. And that whole thing continued basically until about 1900. And one of the things that had happened by that time was, well, Boltzmann had worked out a bunch of things about what would happen in different kinds of systems if one approximated energy as coming in discrete lumps. And that was but he only did that as sort of a mathematical convenience. Okay, then one of the obsessions of the 1800s had been to prove the second law of the thermodynamics, to prove that it was an inevitable consequence of the laws of mechanics that systems with large number of molecules and things would, even if they started off in an orderly fashion, would become more and more disordered over time. But there was just no success. There were lots of kind of interesting things developed, but there was no kind of slam dunk success in proving that fact. From the laws of mechanics determine the laws of thermodynamics. And for Boltzmann, that was through the atomic theory. Not everybody believed that theory, but that was the leading way to sort of imagine going from mechanics to the second law of thermodynamics. I will say, in a sort of, well, maybe more than footnote to this history, I myself have been sort of interested in the second law of thermodynamics for more than 50 years now. And I think I finally understand how it really works. It's a whole story about computation and so on, but that's taking us off the track of talking about the history of quantum mechanics. So back to the history of quantum mechanics. So there was this theories of heat and so on, big interest in proving the second law of thermodynamics. Okay, so along comes a chap called Max Planck, who was a pretty kind of mainline thermodynamicist, German thermodynamicist in the late 1800s. And one of the things that had been observed was this notion of radiant heat. So heat, you heat a thing up, a bar of iron or something, and it's hot, like red hot, for example. But then people had noticed that heat could be transferred radiantly. So that red hot bar of iron, just by the very fact that it's red hot, it was radiating something that could heat other things. There was some way in which heat could be radiated. And that notion of what radiant heat was a big mess. So people imagined that heat was this thing they called caloric fluid, which was some kind of fluid that suffused substances and led to them being hot. And to account for radiant heat, they had to have all these things about how it's a radiant form of caloric fluid, and was a big, complicated mess. The thing that was surprising was, even though kind of the description of what was going on with radiant, caloric, and other things was nonsense, the mathematics that came out was perfectly adequate. And in fact, pretty much the same mathematics that comes out once you have a more correct theory of what these underlying constructs really are. Well, so by 1900, there had been a bunch of experiments done on so-called blackbody radiation. And what that is you have just an oven or something, and it's all coated, it's all black inside, and you heat it up. And somehow there ends up being radiant heat inside your oven. And the question is, what is that like? And the thing that was most notable was the frequency spectrum of what was generated. So, you heated your oven up to, I don't know what, let's say 500 Kelvin, something like that, 200 degrees centigrade, something like this. You would be able to detect that there was electromagnetic radiation of a certain frequency in your oven, that there will be a certain distribution of energies of distribution of frequencies of what was coming out of the oven. So you could heat it up so much that it got red hot, white hot, blue hot. You would get this spectrum of frequencies of light or infrared or something in your oven. Okay, the question was, what was that spectrum? And one thing one could do is to say, well, that's produced by the heat in the walls of the oven is sort of somehow interacting with the electromagnetic field, because people knew about the electromagnetic field. That had been something that from Faraday to Maxwell, it was quite well established that there was this electromagnetic field that could be described as this amount of electric field, this amount of magnetic field. Light was understood to be this kind of oscillating amounts of electric and magnetic field. That had been predicted by Maxwell's equations from the 1880s and 1870s. And then Heinrich Hertz had said, well, if that's the case, it should be possible to generate a traveling electromagnetic wave just by having like a spark would generate some electromagnetic radiation that could propagate through free space, just like light propagates through free space. So he tried this. This is Hertz. And he tried this, and needless to say, he managed to get something where he had a spark generating electromagnetic radiation, and he could pick up some signal from that electromagnetic radiation somewhere else. People asked him, why are you doing this? It's, what's it going to be useful for? He said, well, it's just sort of basic research about Maxwell's equations. Of course, what he had invented was what became radio. And this idea that you could have an electrical effect that produced electromagnetic radiation that could propagate to somewhere else, that's radio. And that was invented, I think, in the mid-1880s. So that was kind of a known thing, that there was electromagnetic radiation. There was kind of that you get different frequencies of electromagnetic radiation from radio down to light and infrared and so on. And the question was, how much of that will be generated by the hot heat in a substance? Well, heat in a substance, if it was caloric fluid, and somehow the caloric fluid had to turn into radiant caloric, and there were various theories about how that worked. But one of the things that was a kind of an idea was that there was some kind of little oscillators this was the thing. By the time you thought that the material was made of atoms, but even if you just said there's an oscillator, because people knew that it was kind of like Hertz's spark gap was kind of like, so you put something electrical in somewhere and you pulse it in some way and it will produce this electromagnetic wave. So the idea was that somehow in this material, there were lots of little oscillators producing radiant caloric, producing electromagnetic radiation. Well, people tried to make that work, and there was a prediction about the form of the frequency spectrum. The prediction was wrong. The prediction was not what was observed. And around 1900, I think Gustav Kirchhoff, had made some pretty detailed measurements of the spectrum. And one day, Max Planck, as I say, mainline thermodynamicist, who believed in caloric fluid, all those kinds of things, realized that if you just took Boltzmann's mathematical calculation of what would happen with discrete packets of energy, and you use that to try and compute what you would expect the spectrum of electromagnetic radiation in a blackbody spectrum to be, well, you got the right answer. And so he fit those curves, and there was a parameter in those curves that he called lowercase h that appears in this distribution, and it's kind of the size of the quantum of energy associated with the electromagnetic field. And so he said, well, we're going to introduce this parameter. He computed its value based on Kirchhoff's experiments. He got roughly 6.5 times 10 to the minus 34 joule seconds, I think. And that constant, the lowercase h, is now called Planck's constant. Its value is actually 6.6 times 10 to the minus 34 joule seconds, but he got it pretty close to right. And he just mentions that in this paper that he wrote in 1900. And that was kind of the place where there was the next piece of discreteness was being discovered. Sort of, well, there's probably discreteness in the electromagnetic field. But the idea that that was sort of associated with atoms and that everything was discrete, Planck didn't want to say that. Planck just said, well, there is this kind of formula that you can get by following Boltzmann's methods, and this is what it is, and it contains this quantity, lowercase h, that is sort of a measure of discreteness of energy, but he didn't really want to go quite all that way. Well, that was 1900, and so then 1905, well, actually 1904, Albert Einstein had been following this track that lots of people have been following to try and explain the second law of thermodynamics. And he had kind of this sort of logical, philosophical argument for the second law that involved kind of this thought experiment about doing this and doing that and so on. Thought experiment not super unlike what Sadi Carnot had done in 1824 when he first came up with things like the second law of thermodynamics, but this was a more advanced version of that. At that time, 1904, Einstein was in the tech industry, so to speak, in Switzerland at the patent office, and the high tech of its time was refrigeration. And so Einstein had been working on refrigerators, even made some patents about refrigerators himself. But so thinking about thermodynamics was sort of a natural thing to do. And the thought experiments he proposed were actually sort of refrigerator-related thought experiments. Unfortunately, they were not correct. They didn't explain the second law of thermodynamics. So his work in 1904 was really didn't really go anywhere. 1905, he kind of took the same kind of thinking, the same kind of logical, philosophical thinking, which, by the way, Boltzmann had been a big enthusiast of. Boltzmann was still alive at that time. He died in, I think, 1906. But I don't think Boltzmann ever knew what had happened in what Einstein did. But Boltzmann himself had sort of given up on the atomic theory. He famously sort of said, one man cannot stand against the tide of history. And he said, I'm going to write down what I know about atomic theory so that, when people finally realize that's what's right, not everything will have to be rediscovered. Sadly, Boltzmann died, a couple of years after that, never knowing that very soon atomic theory will be reborn and the things that he worked out would indeed be highly relevant. But the 1905, Einstein worked on three things. He worked on relativity, he worked on Brownian motion, and he worked on the photoelectric effect. So the photoelectric effect, well, but Brownian motion was this phenomenon where little grains of that were ejected from pollen had been observed by Robert Brown in 1833, I think. Under a microscope, you could see that those little grains were just getting kicked around, and nobody really knew what that phenomenon was. And Einstein, and I think slightly before him, Smoluchowski, had said, well, that's probably actual water molecules kicking these pollen grains. And then they had tried to do a calculation of that, and it had worked out that, yes, that really was what was going on there. So that was a piece of good evidence for the discreteness of matter. Well, meanwhile, Einstein's third paper was about the photoelectric effect. So the photoelectric effect had been observed that if you shine ultraviolet light on certain metals, you would get an electric current. You get so it's sort of as if, oh, by the way, another important piece of this picture, 1897, J.J. Thomson discovers the electron, discovers that electricity is made of discrete particles, and that you can get, for example, you can make a cathode ray tube where you're streaming these electrical particles through the vacuum, and they're sort of landing on a screen which can get illuminated. That's how old televisions, oscilloscopes, computer displays used to work. Well, so 1897, electricity is discrete. 1900, kind of this, well, you could have some sort of, the implication was you could have some sort of discreteness in the electromagnetic field. And meanwhile, from Brownian motion, it's like molecules seem to be discrete. Okay, so then 1905, Einstein is trying to figure out the photoelectric effect and says, well, one way that you could have the photoelectric effect is if there were photons, if there were discrete particles of light, and that the photoelectric effect was a particle of light kicks an electron, a particle of electricity, out of wherever it was and makes it a piece of electric current that is a moving electron, moving piece of electricity. And so from that, he then noticed that if you took Planck's constant, found from fitting blackbody radiation, and you took the frequency of the light that was the ultraviolet light that was causing the photoelectric effect, that, well, if E, the energy of the photon, was equal to H times the frequency, nu usually, if E equals H nu, then you could explain the photoelectric effect. In other words, that there was this relationship that used the very same constant that Planck had identified in the blackbody spectrum, and used it, and the interpretation, which would then fit with the blackbody spectrum, was exactly that there were particles of light, and that there was a discrete, that there was a kind of each particle of light had an energy that was associated with its frequency. So that was kind of the origin of photons, and Einstein's paper about the subject really starts in a very philosophical way, saying we know about the electromagnetic field, we now know that that matter is discrete with atoms from things like Brownian motion. We now know that electricity is discrete. So why don't we imagine that the electromagnetic field will also be discrete? Does that work? Well, look, we have this stuff from Planck and so on. So that was that. Okay, there was another thing going on, which was about atomic spectra. So people had observed that different things like gases, for example, if you heated them up, they would emit light at particular frequencies. And similarly, if they were absorbing light, they would absorb light at particular frequencies. It was as if somehow there was something discrete about the way that light was emitted or absorbed by the material, atoms, in things like gases. So atomic spectra have been observed. The fact that there were these discrete spectral lines, there were these discrete, in hydrogen, for example, you can have a situation where you will have emission from hydrogen that is at this frequency, that frequency, that frequency. It happens that in hydrogen, the main sort of series goes roughly like 1 over n squared, but there's and then it's all the differences between 1 over n squared for every value of n those are the different spectral lines that show up in hydrogen. Okay, so people had seen that. It's like, why does that happen that way? Well, the other question was, well, what are atoms made of? We have this idea there are discrete atoms. We now know there are electrons. What else? What's in atoms? So the next big thing that was discovered was Ernest Rutherford discovered the atomic nucleus. And so what he was doing, well, okay, there was a different piece, which was the discovery of radioactivity, and by people like Marie Curie and so on, Becquerel, discovered, this was around the 1890s, discovered that there were, that you would get that something like radium was radioactive. That is, that you start with radium, and after a while, you have a different chemical element. It had been sort of thought that chemical elements were, once you have that element, you were done. It would never change into another element. I mean, back when the alchemists were in business in the Middle Ages and so on, the big goal had been to convert lead into gold, to turn one element, lead, into another element, gold. That kind of fell into deep disrepute, and people thought elements are forever, so to speak. And then radioactivity was discovered. It was discovered that an element like radium could decay into other elements after a certain amount of time. So radioactivity was known, and there were these that caused one to know that there were these radioactive particles. There were these particles that were emitted when there was radioactivity: alpha particles, beta particles, gamma particles. Alpha particles turn out to be helium nuclei. Beta particles turn out to be electrons, and gamma particles turn out to be photons. But anyway, so Rutherford had alpha particles, which he got from a radioactive source. And then he he could concentrate the alpha particles so they were all going in a straight line. You could do that with an electric field. That's how cathode ray tubes worked with electrons and so on. But he did that with alpha particles. And he kind of, sort of ran them through a gas. And what he found was most of the time, the alpha particles just go straight through. But occasionally, the alpha particles were scattered at a large angle. And so the question was, why was that happening? And what Rutherford figured out is that's because there's a hard bit inside the atoms, the nucleus. And when the alpha particle hits the nucleus, it's sort of momentum conservation causes it's scattered through a large angle. Otherwise, it's just going through sort of more or less empty space in the atom. So that led to the idea that, well, there were electrons in atoms and there was a nucleus in atoms. And the thing that was different between different elements was the structure of the nucleus, number of protons, and so on. Protons weren't yet known, but that was, let's see, that was then there was sort of the question, well, what are atoms like? And there were the kind of these jelly models of atoms where they were kind of like, well, there was an atom and there were sort of electrons that were stuck in this kind of jelly that formed the atom. Thomson had a model of the atom that was like that. Okay, well then along came Niels Bohr, who was kind of a creative Danish physicist, and he had this other model of the atom in which he said that, well, actually there is the nucleus and then there are sort of electrons around the nucleus, and there were certain rules, he said, for certain discrete states of the electrons. He had that idea of discrete states for the electrons to explain atomic spectra, because atomic spectra had these discrete lines. And the question was, what was leading to those discrete lines? And he said, well, it's because the electrons in an atom can only be in discrete states. And those discrete states, for example, for the hydrogen atom, this lineup of these discrete states, and it's because you're seeing transitions between those discrete states that you see the spectral lines that you see. Didn't really explain why there were these discrete states, but he invented a bunch of rules for what the discrete states might be. So that was sort of the next stage. Then the question was, well, why are there these discrete states? What's going on there? And that's when we get to 1925, I think, and Erwin Schrödinger and Werner Heisenberg a little bit later. But Schrödinger had this idea, well, what if these electrons have what he called a wave function. And what if, in fact, what's going on is that inside an atom, he said, well, how do you get discrete stuff out of something where there's just sort of electrons hanging out somewhere? Well, he said, well, here's an example of something discrete that you get. If you have a string that you can pluck and you've got it locked at the two ends, you can have a string that is bowed once in the middle, that bowed twice, bowed three times. You have the modes of the string. You have the harmonics of associated with the playing of the string, and there are a discrete set of these. It's discrete in the sense that there's you can just have sort of one hump, two humps, three humps, and so on. So maybe that's what's going on in atoms with electrons, that you're kind of seeing discreteness because there's a wave function that is continuous, but you're seeing these particular modes of the wave function because you have essentially these boundary conditions that are locking it to have to be in this form or that form. And so that was Schrödinger's idea. And he came up with an equation to describe how the wave function would behave. It's a particular form of equation. And that equation, when you kind of say, well, what would that equation? It involves a potential. That means the sort of a force term associated with, for example, an electric field, as one might expect would exist in an atom if there was a charged nucleus and so on. Electrons we know are charged. And so then he worked out, given that, he worked out what would an atom be like. And turns out it fit what atoms were thought to be like. Well, meanwhile, that was sort of an interpretation involving wave functions and so on. Werner Heisenberg came up with a thing he called matrix mechanics. And matrix mechanics was a little bit more directly, let's look at the states of an atom. Let's just look at these things which correspond to the electron in this state, that state, that state. And let's have those be kind of the elements of a vector. We say it's in this state or it's in that state. And then we say there are sort of transitions between these states that are associated with matrices. And that turned out there was sort of a formalism for, okay, well, you apply this matrix and you keep applying it, and there's sort of an equation that describes it. It's a continuous differential equation again that describes the application of this. Well, for a while, there was sort of this question of, well, should you think about it in terms of Schrödinger's wave mechanics or Heisenberg's matrix mechanics? It became clear quite quickly that they were equivalent. They're just two different versions of sort of the same story. But there was this idea of a wave function. And that idea of a wave function was where you would observe only certain features of the wave function. You would observe these, oh, is it in this state where it's one hump, two humps, whatever? That was represented in matrix mechanics in a slightly more direct way. But this idea arose that quantum mechanics is about the story of these discrete states, and that underneath quantum mechanics was sort of this continuous Schrödinger equation thing that was made discrete in the same way that the modes of a string are made discrete. So, but then, well, then there was a question of, well, what does the wave function on its own mean? And what, for example, if you're not in a hydrogen atom where there are these discrete states, but you're, for example, doing a scattering experiment where things are sometimes reflected, sometimes transmitted, and so on, what is the bigger picture of how you can use this wave function? And along came Max Born, and he said, well, why don't we just say that the square of the wave function is the probability? So in other words, you say you do a scattering experiment, you can describe it in terms of the wave function. That's the underlying quantum description. But what we actually observe, for whatever reason, is we do many experiments and we get different results, different times. But the probability to get a particular result, Born said, is the square of the wave function. And why is that? I mean, what usually when you have probabilities of things, you say there's an underlying thing going on. We don't happen to know everything about it. So we end up with only being able to say there's a certain probability. But in this case, it was like there's fundamentally probabilities. And that's the so-called Born interpretation. Well, it's the Copenhagen interpretation, and then the Born rule. The Copenhagen interpretation from Niels Bohr being, at that point, had started the Niels Bohr Institute, which was funded by a beer company in Copenhagen, still exists today. Don't know if the beer company still exists, but the institute still exists. And that was sort of a center of the early development of quantum mechanics. And this Copenhagen interpretation, the square of the wave function is probability, and that's kind of and then the Born rule is the specifics of that correspondence. Nobody really understood why it worked that way. Still don't. I think we're beginning to have some idea, but that kind of got quantum mechanics to 1925. Another thing that was discovered around that time was electron spin. It was discovered that again, in the story of discreteness of things, it was discovered that electrons in atoms, for example, there would be these. You could sort of account for these different energy levels in atoms by how excited the electrons were, how much, whether they were in the lowest mode, like the string thing, or the next mode, and then what their orbital angular momentum was, what essentially kind of, although this isn't really what was going on, sort of how much they were kind of, were they sort of going around the nucleus sort of at one level or at another level, as in how much going aroundness, how much angular momentum was associated with them. But that was also quantized. Then there was the idea that what was seen was there was additional splitting, hyperfine splitting it was called, between different atomic spectra. When people measured these atomic spectra, they noticed there was just lots of atomic spectral lines were broken, or energy levels were broken in two. What was that? Well, it was realized that that was electron spin. It was the spin, was the thing, the electron spin essentially pointed up or down relative to, for example, a magnetic field that the atom was in. And then there was a thing called the Stern-Gerlach experiment that was, I think, 1930-ish, that in which you have beams of electrons, and you notice that in a magnetic field, they're sort of split into the ones that were sort of spin up and the ones that were spin down, and they kind of go into two different clumps. And so that was then realized yet another thing was discrete. The spin of an electron was again discrete. Well, actually at the time, and this is sort of a important topic for me, is people also thought space was discrete, but they couldn't make that work with relativity, and it was sort of an idea that was abandoned. And 100 years later, we brought that idea back to life, and turns out that's discrete too, just like all these other things that turned out to be discrete. So it was kind of a 100-year detour of space being continuous, and now realizing that we actually do have this sort of computation-based formalism that allows us to understand space as discrete. Just to say a little bit more about the history of quantum mechanics, in the 1920s, there was things like the uncertainty principle, and kind of the interpretation of quantum mechanics in terms of classical mechanics. Classical mechanics was pretty well developed by that time, and there was a whole set of mathematical methods for dealing with classical mechanics, particularly so-called Lagrangian mechanics, in which you're looking at a mechanical system in terms of its degrees of freedom. So, for example, you might have levers and pulleys and things, and you say the lever is in this position. It has a degree of freedom that says what's its orientation. Or it has sort of two important characteristics. Where is it? What is its position, and what is its momentum? Where is it, and how fast is it going? And so those became the so-called canonical coordinates that describe mechanical systems, usually denoted P for momentum and Q for position. And there's a whole theory of Lagrangian mechanics that's based on so-called canonical coordinates. And in classical mechanics, there are things called Poisson brackets, which are basically, it's roughly PQ plus QP, and it's a way of it's kind of a way of describing Newton's laws of motion in kind of a formal mathematical way that works with these canonical coordinates. So what happened, Heisenberg came up with the idea that you could actually think about sort of generalizing classical mechanics, which had certain ways of combining canonical coordinates, to quantum mechanics, that you would just replace these Poisson brackets by so-called commutators, and that you would get kind of and that was sort of the uncertainty principle. PQ minus QP is equal to I times H bar, where H bar is Planck's constant over 2 pi. And that became the uncertainty principle, which became the story of how you can't simultaneously measure both the position and the momentum or the energy and the time associated with something. And that was sort of mathematicized in this kind of uncertainty principle idea with commutators and all that kind of thing. Another thing that came at that time was Wolfgang Pauli's exclusion principle that said two electrons can't both be in the same state in an atom. And that was important for explaining kind of how it was the case that, for example, as you put more electrons into atoms, for example, you go through the periodic table where you have elements with progressively more electrons in them, why it was that the subsequent electrons that you put into those atoms had to be in higher energy states. And that's sort of the key thing that leads to chemistry, is the fact that you get these kind of so-called shells of electrons where the electrons are forced to be in higher energy states. That's because of the uncertainty principle, which Pauli came up with, which just sort of asserted that you can't have two electrons in the same state. That was subsequently mathematicized when quantum field theory was developed. Well, actually, with the Schrödinger equation already, you could mathematicize that by talking about if you have the wave functions for different electrons, that you can only have these antisymmetric combinations of wave functions to describe these systems. So another thing that happened, I think this was 1931, if I'm remembering correctly, was maybe 27. I might have my dates off by a few years here. Was Paul Dirac coming up with the Dirac equation. So the Schrödinger equation purported to be an equation that would describe the wave function for quantum particles. But one question was, what happened when those quantum particles were relativistic, were traveling close to the speed of light? Well, that needed another idea, and that other idea was introduced by Dirac, and it's a different form of equation. In the Schrödinger equation, time and space are treated very differently. In the Dirac equation, time and space are treated sort of comparably as they are in the standard formalism of relativity. Dirac equation implied the existence of antimatter, that was, and positrons, as well as electrons and so on, just as a matter of the mathematical structure of the equation implied that in addition to there being a wave function for the electron, there must also be a wave function for the anti-electron. And then a few years later, the positron was discovered experimentally from cosmic rays after several other particles had been discovered. Then around the same time, this is now late 1920s, the quantum field theory started to be developed. The question was, if you had, in a Schrödinger equation, you're just describing one particle. And you might say that particle is in a potential field, so to speak. It's like there's an atomic nucleus, it's producing an electric field, the particle is in that electric field, and that was sort of a particle in a potential, was what the Schrödinger equation is really describing. But what if the field itself is quantized? What if you have to describe the aspects of the field itself? And that was what led to quantum field theory. It was a bit of a mess at the beginning. It actually stayed a mess for a long time, because the idea was, if you have in the Schrödinger equation, it's like one wave function for one, there's a psi of x, y, and z or something, and time that represents the wave function for an electron. If you have another electron, it's psi2 and psi3 and so on. You have separate wave functions for each electron. And so you have a system of differential equations. It's a coupled system of differential equations representing the relationship of the wave functions for all those different electrons. Well, what if you have an electromagnetic field where you have photons in that field, but photons can pop in and out of existence? You can change the number of photons. How then do you formulate something like quantum mechanics? And that led to the idea of what's called a Fock space, after a person named Vladimir Fock, a Soviet mathematical physicist. And the idea there is that let's see, the original idea in quantum field theory was the following. Imagine that you can have states that correspond to the one photon state, two photon, three photon, four photon, and so on. You've got all those possible states. And what you're then describing using a matrix mechanics kind of idea is what the occupation number in each state is. So you say there are those states, they in principle exist. There might be nothing in one of those states. The three photon state might just not be present. And to describe the fact that we really mostly have 4 photons, we say the 4-photon state exists and has a certain amplitude, and the other photon states have no amplitude. So then we just have a 4-photon state. Well, so the idea was that quantum field theory became a description of how these different sort of modes of the quantum field with different numbers of quanta in them, different numbers of photons, for example, in them, will be related. And there are, so one of the things that happens is there is an uncertainty principle for the number of quanta that you have. And so that's why you have 0-point fluctuations, because you can't know for sure that you really only have 0 quanta. There's always some amount of fluctuation. And this is a longer story. I could perhaps tell this at some point about kind of the foundations of quantum field theory. But one of the things that so quantum field theory was mathematically really complicated, still is. Quantum mechanics, the story of one particle at a time or a few particles at a time, a bit more mathematically understandable, fairly traditional kind of study of differential equations and so on. But there was a lot of question about the interpretation. What did it mean? What did this wave function actually mean? Hence the Copenhagen interpretation and so on. Well, into the middle of all of this came John von Neumann and some other people in the 1930s who decided they would sort of mathematicize this whole story. And they would try and sort of make this notion of, oh, there are these quantum states and there are these measurements that can be done on quantum states, and tried to set it up to be kind of a full mathematical theory. The idea of things called density matrices and so on came in. That was sort of a way of combining quantum states. The idea of states, superpositions of eigenstates. The eigenstates are these kind of modes like the 1 hump, 2 hump, 3 hump kind of thing from the Schrödinger equation. How do you have something which is a superposition of multiple ones of those different eigenstates? And there was a whole sort of mathematical theory developed about this. So that was a perfectly successful mathematical theory. By the 1940s, there were all kinds of issues with quantum field theory and with working out things in quantum field theory, particularly quantum electrodynamics, the theory of electrons and photons. And that was, there were a bunch of problems with infinities where you would calculate the effective mass of the electron based on its interactions with photons, and oops, it's infinity. That already existed in classical electrodynamics by having an electric potential that was proportional to 1 over r, the radius. And if the radius of the electron was 0, which is what one was assuming, then that would be infinity. That kind of phenomenon has a different version, but occurs again in quantum field theory and in quantum electrodynamics. That problem was kind of swept under the rug successfully by my friend Dick Feynman in the 1940s, late 1940s, 1948 maybe, by the idea of renormalization. We can talk about that separately. Dick Feynman never really believed in that. He always thought it was a sweeping the problem under the rug, which it is, but it's a good sort of philosophical way of thinking about it. Anyway, and then along with that, the idea of Feynman diagrams, the idea of being able to compute things in quantum field theory, that showed up. Lots of other things developed. We can talk about that perhaps if people are interested. That's going into the later history of quantum mechanics and quantum ideas. Really, by the 1980s, the sort of formalism of quantum mechanics was, well developed, and it was mathematicized and so on. Sort of philosophically, it was still a bit of a mess. What was this probability? How intrinsic was probability in quantum mechanics? What were sort of phenomena that you couldn't explain on the basis of there being some underlying reality and so on? It all got rather confusing. Then into the middle of that, and again, I can talk about the history of that because I was involved in it. In the early 1980s, kind of the things that became quantum computing started off, and there was sort of, let's take the idealizations of kind of the theory of quantum mechanics and let's kind of build on those, and let's think about doing computation on the basis of those mathematical representations and idealizations. And that's what led to sort of quantum computing, quantum information, and so on. Still didn't really resolve the underlying kind of questions about how does quantum mechanics really work? What's the real mechanism? What's the mechanics of quantum mechanics, so to speak? I think finally our physics project, last few years, we actually do have an understanding of something about what the mechanics of quantum mechanics is. It's not, the I's are not dotted, the T's are not crossed. There's much to still figure out, but I think conceptually we sort of understand how that all works. And it really depends on yet more discreteness of space, discreteness of the paths of history for the universe. That, in the end, is giving one sort of an understanding of quantum mechanics, but maybe that's for another time, although I'm happy to go on and chat about that. Let's see. All right, looks like there's some questions about quantum mechanics. Let me try and address those. What's the craziest historical debate between physicists about quantum theory? Oh boy, I mean, I think they're sort of peeled off this kind of philosophical strand about quantum theory and this whole sort of hidden variables thing, people like John Bell, David Bohm, this is 1950s, kind of trying to understand what the sort of interface between sort of the philosophy and the physics of what was going on was. That was kind of a feature. I mean, things changed by the 1980s. That's a different story. Memes is asking thoughts on extending Kirchhoff's black body experiments to astronomical bodies. Well, I mean, we know the temperatures of stars because we see their spectra and we believe we understand black body spectra. That's about all we can say. We don't have the independent ability to go visit the sun. If we got very close to the sun, it's at 6,500 degrees or something Kelvin on the surface of the photosphere. We could, in principle, go there and get a piece of plasma and sort of measure its temperature in a different way than from its radiation effect. But that's not what anybody imagines doing. One really understands, I think, at this point, black body spectra and radiant heat pretty well. Freeman asks, was the Copenhagen interpretation a mistake in regard to how paradoxical results were glossed over? Physicists didn't care about it. For physicists, it's like we are computing so-called scattering amplitudes, probabilities of different kinds of outcomes of scattering experiments. Scattering experiment is basically you fire a beam of particles at a target or at a beam of particles coming in the other direction, and you see how things get scattered away. Basically, for people who kind of grew up post probably 1930s, it was in physics, it was kind of just like, well, you compute scattering amplitudes. That's what you compute. You compute probabilities of things. The question of why are they probabilities was of interest to a tiny minority of kind of philosophically oriented physicists and physics-oriented philosophers. So it was just irrelevant. It wasn't really something people concentrated on. The question of sort of why it's true and how it works has been quite muddy. I mean, I think now we have a pretty nice understanding, and I'm slowly getting to the point where I think we're going to have a really crisp way of explaining what's going on. And it's roughly, there's this notion of branchial space, the space of all possible quantum branches of history. And one of the key things I've only really internalized recently is that just as all of us observe the universe from our perch on this particular planet, so all of us observe the universe from a particular place in branchial space. And so the reason that we think that definite things happen and we agree about what happens is we're all nearby in branchial space. And we can't know what will happen necessarily. It's still unknown and probabilistic because we can't anymore determine where we're going to be in branchial space on some theoretical basis than we can determine that we're going to be on this particular planet theoretically. Why do we exist on this planet rather than on another planet? That's something we happen to be on this planet. It's not something for which there's a theory that we will derive that we're on this particular planet. But we can derive certain features of what kind of a planet we might be on, and that's where we start to be able to make statements. And what I think features of what kind of an observer we can be will give us more information, already has given us a bunch of information about how things work. The fact that we are computationally bounded, we are a bounded extent in branchial space, already has a bunch of implications, already leads us to this idea of emergent reality in quantum mechanics. So that's, I mean, I think I'm pretty excited that, after 100 years, we finally actually have sort of a more mechanical version of quantum mechanics, where we can really understand from sort of more from the ground up what's going on. Okay, Popo is asking, can you tell us more about Schrödinger's cat? What is actually happening? Well, so that's going to get a bit into physics, but I'm going to say a few things about Schrödinger's cat. So the issue is that in the formalism of quantum mechanics, there are, when you say we have measured, we as observers, humans, whatever, said this is what happened. Okay, we can say the electron went that way, the electron went this way, the photon went that way, the photon went this way. We know what happened. We are certain we know what happened. In the formalism of quantum mechanics, in sort of the innards of a quantum process, there are merely a superposition of those possibilities. In the innards of the quantum process, it's kind of doing its mathematics based on there being, well, it could have gone that way or it could have gone this way. But we have to consider both possibilities, and we have to carry along these quantum amplitudes, these different possibilities, and these different possibilities can sort of interfere with each other when it comes to sort of what's happening inside the quantum process. It's only when we get to measure it, when we get to sort of humanize what happened, that we conclude that something definite happened. Now, in my view of these things, what's really happening is there are many threads of history that are really happening sort of at the quantum level. But we believe that definite things happen. So for us, in our minds, we have to knit those threads of history together to conclude. We have to sort of say, well, we're just going to assume that these threads of history are somehow consistent, so we're going to conflate them together and come out with a definite conclusion. And that is the process of measurement. But in our models, something which really hasn't been the case before, you start to be able to get inside that process of knitting together these threads of history and conflating them so that you get one definite result. And that's kind of the mechanism of quantum measurement, which we're now just starting to understand. Okay, back in the day, Erwin Schrödinger, he was talking about the idea that what counts as the innards of a quantum process versus when you measure the quantum process. Why is it? How can it be? What is that thing that happens when you do measurement but hasn't happened in the innards of the quantum process? So people got very confused. You say, well, you've got this quantum process, it's happening in this box. We don't really see what's happening in the box. So it's still quantum process, interference of different quantum amplitudes and so on in the box. It's only when we open the box and we are kind of attaching it to ourselves as observers that we get a definite conclusion. Okay, so Schrödinger said, well, what if what's in that box is a cat? And the cat, I don't know how he particularly formulated it, it has all kinds of unfortunate ends, but the cat might have, depending on whether a photon goes this way or that way, the cat is shot, the cat is, who knows what. Anyway, the cat might be dead. And what Schrödinger said was, well, that's a very bizarre thing, because we know that a cat is either dead or alive. It can't be sort of half dead, half alive. It's got to have decided, is it dead or alive, even though we didn't open the box. Something definite had to happen. That was his argument. Now, the fact is, it's a squiggly argument, because the reason he picked a cat, dead or alive, is that you can't imagine it being intermediate between being dead and alive. Let's say he said, well, we've got this vial of water in there, and the water might be steam or it might be liquid water. But, and depending on what happens, it's either steam or it's liquid water. Well, you could say, let's say we've got a lever and it's flipped one way or the other way. we kind of know that there could be an intermediate. The lever could be vibrating back and forth. The water could be above its critical point where there's no distinction between the liquid phase and the gas phase. There could be some intermediate case. But he said, let's make it be a cat that's dead or alive, because one imagines that it's definitive. It's either dead or it's alive. It's not in some intermediate state. So what he was kind of pointing out was that this process of quantum measurement, is that sort of happening in the character of the cat, in the innards of the cat, so to speak, or is that only happening when you open the box and you're kind of connecting it to us humans? So actually, in our models of physics, as I think about it, we could actually analyze that, because we actually have, because we know something about the mechanics of the measurement process, we can say, is there an effective cat in our system that is kind of concentrating things so that it is like a measurement process, or is it merely these quantum branches just going along as they merrily were? So we can actually analyze, is there some cattiness, so to speak, to the whole situation, where instead of it being the case that all these quantum branches are sort of interacting in the usual way, it could be that they are concentrated into these sort of mega threads of sort of the cat being alive and dead. But so that's a rough story of the Schrödinger cat. Let's see. Harry comments, aren't zero-point fluctuations an absolute rest frame and therefore a fatal blow to relativity? Ah, yes, a can of worms. I think this finally gets resolved in our theory of physics, and then the way that space-time or space emerges from what amount to the effects of these quantum fluctuations. But yes, it is a mess, because when you describe a quantum field, yeah, this is such a mess. In the description of a quantum field, as I mentioned, a quantum field is this collection of possible in the so-called Fock space interpretation, Fock space representation. It's a combination of the 0 photon, 1 photon, 2 photon, 3 photon, but each one of those modes, which actually has a half unit of occupation number, that's a consequence of the uncertainty principle, each one of those modes has a little bit of something going on in it. You can't say it's absolutely zero. And that little bit of something going on is vacuum fluctuations of a quantum field. You can actually measure those vacuum fluctuations in a thing called the Casimir effect, for example. If you take two metal plates and you find that there's a small force of attraction between them, basically because sort of all the modes of the quantum field exist outside the plates, but between the plates, certain modes aren't allowed, because modes that would not be fit in this kind of string analogy, modes that wouldn't fit between the plates aren't present between the plates. So there's sort of more modes on the outside than there are on the inside. And so there's this force between the plates. That interpretation of how the modes work isn't quite right. As you discover, if you try and make a box, you'll discover that that it no longer, all the pieces attract. But it's a rough picture of what's going on. But so one of the issues is, in the usual description of we've got these modes of the quantum field, they're just sitting there, and it's like the modes exist, and we can either have particle something exciting those modes or not. Well, in the usual way this would be set up, those modes would just exist in space, and they would be, we got a mode of the field, it's here. We got another mode of the field. They define a notion of being at rest. So actually, what's really tricky is if you accelerate relative to a quantum field, you actually start generating particles. So an accelerated observer observes different particle content than an observer at rest in a quantum field. That's a weird thing. It's oh my gosh, Jacob Bekenstein was involved in that, and Rindler, Wolfgang Rindler, I think. It's another person involved in that. This was a thing, this idea that the particle content of a quantum field is not, depends on how accelerated you are. Essentially what happens is, if you're an accelerating observer, you're kind of what counts as one mode versus another, and this occupation number of modes gets transformed by the way that you observe the quantum field. What consequences does this have? Well, it's what leads to Hawking radiation, for example. It's what leads to the fact that in the gravitational field of a black hole, you end up getting this kind of radiation. The particle content is not what you thought the particle content was. Effectively, you're generating particles from the vacuum. And the same thing happens to an accelerated observer, which also happens to have an event horizon just like a black hole. Again, a slightly complicated story of general relativity. But that's so the notion of particle content depends on observer reference frame. And so in the end, there is a sense in which the vacuum fluctuations of a quantum field define a reference frame for the universe, just like the cosmic microwave background does. The idea from the Michelson-Morley experiment in 1900 that there was no ether drift, that is, it was thought at the time that the electromagnetic field, like a sound wave, is compression and rarefaction in air. An electromagnetic wave was some kind of distortion of the ether, some mythical substance that sort of pervades the universe. So what was observed was that there was no ether drift, there was no kind of change in there's no ether wind associated with where the Earth was in its orbit and so on. And so people said, well, there's no preferred reference frame. And that's what led Einstein in 1905 to kind of his axioms, which led to relativity, include there is no preferred reference frame in the universe. Well, it turns out that it just isn't true. There is a preferred reference frame in the universe. It's defined by the cosmic microwave background. And we can say the Earth is moving at about 1,000th of the speed of light relative to the cosmic microwave background. The cosmic microwave background is kind of the center of mass frame of all the content of the universe. Well, the vacuum fluctuations of the 0-point energy is a similar story, probably, to the cosmic microwave background, except you don't really need that story in our models, except this isn't properly worked out. We should work it out. Because in our models, the vacuum fluctuations are what create space-time. There are these discrete atoms of space that have these relations, and it is the fact that there are transformations of these relations between atoms of space that leads the atoms of space to kind of be knitted together to make something like space. It is the quantum fluctuations, basically, that make the structure of space. So the same kinds of issues don't occur, and that's kind of the beginning of that story. Let's see. Louise asks, did Feynman's work on quantum electrodynamics completely change the game, or was it just building on others? So, well, what happened was people wanted to compute quantities in quantum electrodynamics. They wanted to work out things like a thing called the anomalous magnetic moment of the electron. Electrons act like little tiny bar magnets, and they have a certain magnetic moment, sort of amount of magnetism associated with them. But that amount of magnetism isn't exactly, it's not what would happen with an electron that doesn't have interactions. It's what's observed is an electron with interactions. It's the G minus 2. G is the gyromagnetic ratio. It's the ratio of the magnetic moment to the angular momentum of an electron, basically. And that is roughly equal to 2 in some units. And G minus 2 is the anomalous magnetic moment of the electron. And that was computed to be 1 minus alpha over 2 pi, if I remember correctly. Is it alpha over 2 pi? I think so. Alpha is a thing called the fine structure constant. The fine structure constant is a thing that characterizes the strength of the electromagnetic interaction. It's kind of, in some dimensionless units, it's the size of the charge of an electron relative to roughly, well, let's see, relative to what? It's not quite relative to the mass. It's relative to the quantum of energy, this H, Planck's constant, and so on. But in any case, the fine structure constant is roughly equal to 1 over 137, and it characterizes the strength of electromagnetic interactions for things like electrons. And so what people wanted to work out, an electron in an electromagnetic field, what will the effect of that electromagnetic field be when the electromagnetic field is quantized, the electron is quantized, what will those effects be? It's a difficult piece of math. The main thing is that in a first approximation, the field has no effect. Then you have to say, well, it has a little bit of an effect associated with 1 over 137. Then maybe it has a little bit more, which is associated with 1 over 137 squared. And you make this so-called perturbation series where you're looking at the thing without any perturbations, and then you're looking at the effect. You're making a so-called perturbation series where you say it has sort of one level of effect, another level of effect, another level of effect. That kind of methodology was developed in celestial mechanics, where people were working out, the orbits of Earth, Moon, Sun, and they were saying, but let's have a perturbation associated with Jupiter, let's say, and you can make the first order perturbation, the second order perturbation, and so on. So there was a well-developed so-called idea of perturbation theory from celestial mechanics from the 1800s. And what then happened was the idea was, let's apply this notion of perturbation theory, this notion of making essentially a series expansion in powers of the fine structure constant. Let's apply that to doing calculations in quantum electrodynamics. So it's like, okay, how are we going to do this? It was a complicated mathematical mess. And there were several people who tried to work on this. A person called Julian Schwinger, who sadly I never met. I could easily have met, but I never did. Was one of them. Another person named Tominaga, oh gosh, Japanese name, which begins with an S, and I don't remember it, I'm afraid. And I never met him either. And Dick Feynman. We're all interested in this problem of calculating kind of the this perturbation series for quantum electrodynamics. Okay, well, Dick Feynman had one key idea. His key idea was to make these kind of diagrammatic representations of kind of so-called space-time diagrams of these interactions. So for Schwinger, he had this thing called source theory, which kind of dug into the mathematics of quantum electrodynamics and represented it in terms of something which was sort of, I think, inspired by methodologies in classical mechanics, these source terms and the effect of a source term and these functional derivatives with respect to source terms and a whole bunch of mathematics, which was pretty hard to understand for most people. So Dick Feynman sort of came up with a kind of physical intuitive story, which was, well, let's just think of these things, these particles, as being these space-time, these things that move through space and time. We can draw a world line for this particle in space and time. We can draw a line representing an electron. And then we could say, well, the interaction is a place where the electron line is, for example, a photon line goes and sort of hits the electron line. That represents the interaction. That's the interaction event. And so we can make these space-time diagrams that show there can be an interaction event here that produces a photon. The photon goes along. Then that photon interacts with an electron later on, for example. It makes a diagrammatic, a space-time diagram of what's happening. That was, I think, somewhat inspired by Feynman's work with John Wheeler as a graduate student in Princeton. One of the things that, well, a piece of that story had been the mystery of why all electrons are the same. They have different energies and momenta, they have the same mass, they have the same other characteristics. And so Feynman had this idea, and Wheeler, I think, also, that electron might be going forwards in time, a positron might be an electron that's going backwards in time. And so the amusing idea was, maybe there's only one electron in the whole universe. It's just zipping forwards in time, backwards in time, forwards in time. And it's really every electron we see is the same electron. It's just been knitted forwards, backwards in time. So that was an idea that they kind of imagined. And I think that may have been part of what led to this notion of a space-time diagram to represent this interaction process in quantum electrodynamics. So that really sort of demystified what might be going on. But then the question was, well, how would you actually calculate the scattering amplitude associated with one of these diagrams? So that led to the Feynman rules, these rules that say, an electron line is, oh my God, it's so long since I thought about this. It's p/-m over p squared is the quantity associated with an electron line. The p slash is a Dirac gamma matrix dotted into the momentum 4 vector, and m is the mass of the electron. That's easy enough. And that is the so-called electron propagator. Actually, a better representation is 1 over p slash minus m. And that's a thing called the electron propagator, and that essentially represents the contribution to a scattering amplitude associated with that electron line. The photon propagator is 1 over p squared times some things to do with epsilons, which have to do with the polarization of photons. And the each vertex is where a photon interacts with the electron. That has a certain, that's a there's a lowercase e, which is related to the fine structure constant associated with that. So everything in these diagrams, there's a piece of math formula associated with it. Now, it turns out that when you have a closed loop in one of these diagrams, that you get an integral. You're saying, well, there are in this closed loop, you can distribute the momenta of the particles any way you want, still adding up to the right thing in this closed loop, and that leads to an integral, and that leads to these so-called Feynman integrals that show up in Feynman diagrams. And working out the structure of what happens with all these different pieces of Feynman diagrams is a big mess. It's a big mess that actually led me, for example, back in the 1970s, that's what got me involved in doing algebra by computer, was working out Feynman diagrams, because they are very algebraically complicated. And by the time the first order diagram may be quite simple, but by the time you're at a diagram with 3 loops and you've got however many large number of integrals over 4 dimensions and so on, you've got sort of 12-dimensional integrals, and it's really complicated. And so I kind of tried to use a computer to do that, and succeeded in using a computer to do that. And that was kind of the but a key thing. So Feynman defined this way of working out sort of the amplitudes from diagrams. There was a problem, which was when you did these integrals, you just got infinity often. So then he had this idea of renormalization, and the idea of renormalization is this: if you have an electron, it has sort of an infinite amount of self-energy. There are photons that can interact with it, and they can infinitely interact with it. But the thing is, every electron you ever see has an infinite number of those photons interacting with it. It has infinite self-energy. So the thing to think about in renormalization is, well, the bare electron, we don't know what its mass is. Maybe its mass is minus infinity. And then when we add in all those photons, they add plus infinity. So we've got the minus infinity bare mass plus the plus infinity effect of all those photons. And then we just say, well, all we know is that the result is the electron mass. And so that's the idea of renormalization, that you can basically say the bare thing without any interactions going on. We don't know what that's like. Might be infinity. That infinity is, it could be a minus infinity. So it cancels out any infinity associated with interactions. So the real issue is when you do that, okay, you say, well, there's this minus infinity for the electron mass, there's a minus infinity for the electron charge, etc. The real question is, are there only a finite number of those infinities? Or is the whole theory, do you have to introduce another infinity every time you work out a new thing? Because if you have to introduce another infinity every time you work out a new thing, you'll never get a definite answer. Well, it turns out in quantum electrodynamics, there are only 3 infinities. There are precisely 3 that show up. And everything, once you've decided, okay, we've got the electron mass, we've decided what it is, we've got the electron charge, we've decided what that is, and there's a third one associated with vacuum polarization. We've decided what that one is, then it's everything that you can work out, you can show the infinities somehow sort of cancel out, and you get left with just those things that we measured. So that's kind of the idea of renormalization, and that's the idea that Dick Feynman never really believed in, but it worked. It worked well, and quantum electrodynamics was well solved in the 1950s. Then QCD became clear that there was a perturbation series for QCD because at sufficiently high energies and high momentum transfers, QCD would behave as if its so-called coupling constant, its analog of the fine structure constant, was small enough that you could do a perturbation expansion. I was much involved in working out things to do with that. But the consequences of that, at least. Then, okay, so Feynman diagram calculations were sort of an early impetus for computer algebra, for the world at large, and for me in particular. It was pretty routine to have to run for a year of CPU time to work out, the next order correction to the electronic anomalous magnetic moment. The results were spectacular. The results agreed to, I think, maybe 8 or 9 decimal places now. You can work it out. It's very complicated to work out, and it nails it. You measure it experimentally, it precisely agrees. It's a spectacular agreement between complicated theory and experiment. Actually, you're sort of limited now because there are effects in the theory that aren't just quantum electrodynamics. There are effects from other kinds of particles and so on that show up. And so you're kind of limited on how much more you can calculate from first principles, so to speak. But in any case, the question of what the main thing was the fact that you can represent quantum field theory in terms of Feynman diagrams and do these calculations, and that you can use renormalization as a way to get rid of the sort of inconsistent infinities. That was kind of Dick Feynman's big contribution in that area. Another related contribution was the thing called the Feynman path integral, which is a way of formulating quantum mechanics, which really wasn't that popular until very recently, but it's a very elegant thing, which actually we can understand very clearly in our models now. I will say that Dick Feynman never thought that Feynman diagrams were a good idea. In fact, I just found something that I wrote in 1979, which has it was actually mostly about sort of practical computer calculation of Feynman diagrams, but I had completely forgotten that I had written kind of a philosophical description about the kind of the philosophy of Feynman diagrams and what one might conclude from them. See, the thing is, in the end, you do all this complicated calculation, and the answer turns out to be 7 minus pi squared or something. And you've calculated 1,000 diagrams, and you've done all of this computer calculation, and then the answer is 7 minus pi squared. Doesn't seem right. Seems like there's got to be a more direct way to get to that, whatever it is. Actually, there's one I remember was 9 minus pi squared, shows up in a particular case. But it feels like there's got to be a more direct way to get there. And I worked out, in fact, I had forgotten that I'd ever written this down, that the kth order of perturbation theory, that the rough order of difficulty in quantum electrodynamics is k factorial to the 5th power. So if you are sort of into computer algorithms and things, that is a horrible algorithm, where as you try and make it more accurate, the amount of computational effort you have to go to increases very dramatically. And so I remember talking to Dick Feynman about this very point, and he's like, look, you've just got to understand Feynman diagrams aren't the right approach. There's a better way to do it. Actually, I recently also found a stack of papers that Dick Feynman gave me sometime when I was over at his house. He said, hey, you're working out Feynman diagrams. He said he'd worked out a bunch of sort of general theory of these Feynman integrals and so on. So let me give you the sheaf of papers, which he did. And they show up, they're in my archives now, and I really need to put them on the web. They're kind of an interesting collection of results about kind of the kinds of mathematical functions that show up in these Feynman integrals, particularly polylogarithm functions, which at that time people really had never heard of. I forget whether Dick Feynman, what on earth he called them. I think he just called them L or something. They were sometimes called Spence functions and sometimes called other things, but they only became popular. I first really got into them in the late 1970s, but I think in the world at large, they probably didn't become popular until the 1990s or so. In any case, the thing that's sort of interesting, even in the things that I wrote, was I had tried to inventory all known Feynman diagram calculations because I wanted to see what kind of regularities existed there. And I found a bunch of regularities of, there are these things which have powers of pi in them, et cetera, et cetera, et cetera. And I kind of got the suspicion that there was some kind of regularity that you could determine from the algebraic structure of these answers. And that's what I said there. And now we're many, many years later, and sort of from string theory comes this idea of the amplitude hedron and this discovery that there are, in string theory, there are sort of versions of string theory, n equals 8 supergravity, that have where the Feynman diagram calculation is kind of easy. But then the question is, can you deduce things from sort of the structure of the results, the kind of functions that occur in the results? Can you deduce things that might also be true for something realistic like QCD or QED, quantum electrodynamics, quantum chromodynamics? And that looks to be somewhat promising. Well, actually, to just bring things up to the present or the future, I recently figured out something in our models of physics that is kind of a way of doing something like Feynman diagrams that is kind of below Feynman diagrams. So Feynman diagrams are representing kind of space-time structure and causal relationships between events, interaction events between particles. I think there is a way of studying that at a lower level where you're dealing with causal events that are really the fundamental causal events of the universe and doing the equivalent of a perturbation expansion on those. That's a coming attraction. I still have to figure it out. But I think we may have a kind of, what should we call them, infra-Feynman diagrams that are kind of things that are below the level of full particles, but they are the same idea as Feynman diagrams. And sort of there are some indications of that in things I was studying in the second law of thermodynamics, studying hard sphere gases and little balls bouncing off each other. You can think of the same kind of thing as these sort of a diagram representing, oh, these two balls interacted. That was an interaction event. What effect does that interaction event have on a subsequent interaction event? That's a Feynman diagram-like thing, I think. So anyway, it's let's see. Well, there's other questions here about quantum mechanics. I think I'm supposed to go back to my day job here, unfortunately. I'll try and there's some questions about the interpretations of quantum mechanics and Wheeler's participatory universe idea, Bell's theorem, and so on. I have to say sometimes, John Wheeler, I unfortunately met him only once. I should have met him many years earlier, but I didn't. I exchanged letters with him. I would have said email, but it wasn't email. It was physical letters, quite a number of times. He was at least by the time I knew him, he was quite a bombastic kind of character. He would have these very sort of, these very exclamation mark filled letters with very kind of dramatic statements and so on. But he has this picture of a big U, which is kind of the idea is the I, the observer, is being created from the innards of sort of a quantum process. I'm not completely sure I understand what he was talking about. And I think it may be related to so-called second order cybernetics, which is kind of the another sort of idea of the observer observing the observer type thing. I'm not completely sure I understand it. I could tell one somewhat sad story. The one time I met John Wheeler in person, he was 95 years old. And I think shortly after my new kind of science book had come out. And I went to see him, and he was kind of a bit quiet, but he's leafing through the book because I guess I'd sent him a copy of the book, and he was like, and eventually he looks up and he says, "You know who should talk to about all this stuff? There's a chap over at this." He was in Princeton University. There's a chap, he said, over at the Institute for Advanced Study, which is a place where I worked for a while, but on the other side of town in Princeton. He said, there's this chap over at the Institute for Advanced Study named John von Neumann. And he sort of started spelling out the name. And I was like, it was kind of a sad moment because I had to say, well, unfortunately, he died before I was born. It's something I have to say, I feel for that situation because, I realized that there are things, remembering kind of what happened when, it's kind of like there's this person, there's this thing, and, it's sometimes hard to remember. There are people, I've known a lot of people who, perhaps because I started my career young, I knew a lot of people who were significantly older than me who are no longer alive. And sometimes it's really pretty hard to remember, oh, there's this person, they were in such and such a place. Oh, unfortunately they died 25 years ago. And, it takes me effort to think of that. So, but it was kind of a sad moment there. But in any case, so I didn't have a chance to really talk to John Wheeler. As I say, we did exchange a bunch of letters, which I have to find and probably put on the web at some point, um, about various things to do with kind of foundational questions in physics and so on. All right, I think I better wrap up for now. I will say that in terms of the history of things like quantum mechanics, it is funny because I got into that business in the mid 1970s, right at a time when quantum field theory was really very popular, very, very much being very successful. It hadn't been successful for quite a few years before that. But I knew many of the people who were still around at that time. And sort of some I never met, like John Bell, for example, of Bell's theorem. I never met him, even though I could have done. But actually, you know what? That can't be true. I'm sure that John Bell was in a small group of people, because I spent a bunch of time at CERN where he worked. And back in, this must have been 1979 or so, theory group there happened to be trying to recruit me. And John Bell must have been in a small audience of people that I gave some talks to and things like that. But I never, to my knowledge, I never talked to him. And certainly at that time, things about sort of the interpretations of quantum mechanics, nobody cared about that stuff. John Bell was talking about some of those things, but John Bell was mostly doing things like accelerator physics and so on, and really not, that was sort of a hobby project that has become very famous subsequently. But at the time, it's like quantum mechanics is just a thing you use in practice. We don't know why it works. The philosophy of it is not relevant. It's a little bit like machine learning today. There's a lot of sort of, let's just use machine learning. Knowing how it works and why it works is kind of a separate problem that is a different branch that isn't of concern to most of the practitioners. It's Weasel is commenting. It's nice that I got to meet these people. I have to tell you one more bad story, okay? So this is probably 1975, and I was 15 years old, and I was into physics, and I was often going to physics seminars, particularly in Oxford, which was near where I went to school. Somebody told me one day, Werner Heisenberg is giving a talk in Cambridge. You should go and see it. And I was young and ignorant, I suppose, at the time, and the web didn't exist. That's my other excuse. So I couldn't really look up. I didn't know that much about Werner Heisenberg. I knew what he'd done in quantum mechanics. I then had the impression, he was working on some unified field theory, and it's kind of and it's all didn't go very well, and I don't really know what it is. And he's an old guy, and he's got some silly theory. And so I'm like, I can't be bothered to go to Cambridge. Actually, the person who told me this said, and Heisenberg always likes to meet the young'uns, so to speak. Well, drat, I should have gone to that. I should have taken that train ride and gone to meet Heisenberg, but I didn't, and he died a year later or so. And what's even more frustrating is that, in fact, I had even got a copy of his book about his unified field theory. It must have been within a year of that time, possibly even I already had it at that time. And I barely opened it. And years later I did, and I realized that it's all about kind of a nonlinear field theory in which kind of particles emerge as things like solitons, kind of nonlinear equation solutions and so on. And it's really very interesting. I don't think it's right, but it's interesting. And it also has a bizarre resonance with things about fluid mechanics. And it turns out, again, I didn't know this. This is one of those things you only learn once the web exists and you can easily look these things up, is that I should have used encyclopedias more. Okay, I didn't, because that probably existed in an encyclopedia, maybe. That Heisenberg had spent many years working on fluid turbulence. And which was a topic I was also interested in. And the interface between that and quantum field theory was something very interesting. It's Anyway, well, thanks for your comments here about quantum theory. Actually, I've never tried to explain the history of quantum mechanics before, so I'm happy that that I think I didn't miss any big pieces, and that was fun to try and pull that together, and a good prelude to the year of the quantum in 2025 for the 100th anniversary of the 1925 progress in quantum mechanics. I will say that I always find it interesting. People think of all these people who are involved in quantum mechanics as old people. But when they did a lot of their work, they were quite young. I mean, they were kind of young eager beavers, although there were some older ones also mixed in there, like Einstein, for example, was older by that point. And Einstein was actually pretty skeptical of quite a lot of what these people were doing. We can talk about that another time, perhaps. But it is always, it always seems very sort of esteemed and so on to imagine what happened 100 years ago. But it was a mess. It was people sort of, like, have you solved it? Have you solved it? Who gets credit for this thing? And a lot of sort of foment that is all lost in the mists of time, so to speak. And I always find it interesting in things I've been involved in that there is sort of an origin time for things. And it has all that messiness of all that, individual people and their various foibles and so on. And then eventually sort of it becomes kind of the Schrödinger equation. And it's just like, that's a thing. Who is Schrödinger? Oh, he was an old guy. Actually, he wasn't an old guy when he came up with Schrödinger's equation. But it's all kind of, the history has kind of become much less dramatic in a sense, or maybe more dramatic. It's become, and this was discovered. Well, actually, it was a messy, complicated process by which it was discovered. And I must say that I find it interesting in our physics project, which I have to say I am completely certain is kind of the paradigm for physics that is kind of the next paradigm after the one that was developed 100 years ago. And we're still in its early days. And it's still in kind of like, oh, there are people working on it, and there's kind of sort of, oh, yeah, well, and there are people who don't really believe in it, maybe, and there are people, all these kinds of things. It's all a lot of kind of foment. In time, it will just be, and then in 2020, this particular paradigm got developed, and by some point in time, it's just that data point in history. All right, I should run off here. Thanks very much, and look forward to talking to you all another time. Bye for now.